Alright, in this video we want to move on to a somewhat interesting, I think kind of fun topic that is, I'm sure, near and dear to your hearts and pockets. This is digital logic, and this is the basis, the very, very fundamental basic principles that virtually all of your devices operate on. Alright, so what I meant by pocket, of course, would be your phone, or perhaps tablet, or whatever. Almost any electronic device, pretty much any electronic device, has this stuff going on in it in some form or another. So this is, again, very, very basic. The things, your actual devices are using what we're going to talk about in this video in an extremely complex manner, but this is the basics. So we're going to talk about digital logic. We're going to talk about what analog means versus what digital means first, and then we're going to talk about the 5 basic types of logic gates, and that'll be it for this video. There will be 2 more videos on the topic of digital logic, so let's get started. First, we just want to establish what does analog mean and what does digital mean. So up to this point, all of the devices and electronics, pretty much most of them anyway, that we've been talking about are analog, and that means that when you apply voltage or current to them, you can vary that. If the circuit has a changing voltage or a changing current, it's going to change smoothly, like a curve. This is just an example of a curve. It's not necessarily any voltage or current that you would find in a circuit that you might ever encounter, but the point of this graph is not to show you any specific circuit, but to show you that this graph changes smoothly, right? It's a nice curve, it's continuous changes, right? It goes up a small amount, down a small amount. It's a smooth curve. You're used to seeing curves like that. That is not what a digital signal looks like. Alright, let's first get the definition and then we'll look at a graph. In a digital signal, the voltage or current varies in discrete, abrupt, what we might call jumps. It is not continuous. It is there are basically only 2 states to a digital circuit, and that's high or low, sometimes called on or off, sometimes represented as a 0 or a 1, and that's what I've got. I've got on and off and high and low as examples of how you might define these, and they're going to look like this. You basically have either your signal is off or your signal is on. There is not a smooth curve in between. It just jumps. Suddenly on, suddenly off, right? So off would be this position, on would be this position of the graph, or you could, these terms are interchangeable. You could say high or on, you could say low or off, you could say 0 or 1. I didn't put those in there, but this would be 0, this would be 1 in your digital binary code. So these are examples of digital signals where for a while it's off and then it's on and then it's off and then it's on. Low, high, low. All right, so that is what a digital signal looks like. That's the difference between digital and analog. Digital, abrupt, discontinuous jumps. It's either on or off. There's no in between. But analog, you can just have smooth, continuous variation of all possible numerical values. All right? Okay, so moving on, let's talk about logic gates. All right, and this slide is just to introduce the terms. In the next couple of slides, we'll look at them in more detail. But basically, digital logic gates are digital circuits that respond to inputs and produce an output. Usually just one output, sometimes just one input, but often it's more than one input into the logic gate. So basically, it's a somewhat complicated circuit, but we're going to just talk about them as if they're a single device for the purposes of this class. So we have 5 different gates. One is called a NOT gate, also sometimes called an inverter. The second one is called AND. Then there's an OR gate. And then we have 2 gates that build on the AND and the OR. This one is called a NAND gate, and this one's a NOR gate. All right, so let's see what those all do and how they work. We'll start with the NOT gate. Here we have the symbol for the NOT gate. It's this triangular thing with a circle at the end, and then a line for the input and a line for the output. So the input we called A, and the output we called Y. So let's just see, what does a NOT gate do? And it's all written out down here in the bottom. When input A is high or on, or 1, logic 1, then the output is low or off, or logic 0, right? I won't draw in the 1s and 0s anymore, but so basically if this is high, this is low, right? And then if input A is low, if this is low voltage, then this is going to be a high voltage after the logic gate has done its work. So if you input a high voltage to this logic gate, what you get out is a low voltage. And if you input a low voltage to this logic gate, then you get out a high voltage. So what does it do? It basically just inverts the input. It reverses whatever you put into it. So if you put in a high, you get out a low. If you put in a low, you get out a high. All right? Really simple for the NOT gate. So let's move on. All right, on this slide we have both the and the OR. So let's start with the AND gate. That's the symbol. So as you can tell, there are 2 inputs for an AND gate, and there's only 1 output. So we've called the inputs A and B, and the output again is Y. So how does the AND gate work? Well, output Y is high, or high voltage, only when both inputs are high. So if A is high, B is high, then Y is high. If A is on, B is on, Y is on. If A is off, Y is off. If B is off, Y is off. And if A and B are off, then Y is off. So basically, the only time that output Y is on, or high, or 1, the only time that happens is when both of these are likewise high. Otherwise, this output is low, or off. All right? That's why it's an AND gate. Both A and B have to be on. A and B both on. That's the only time that Y is on. An OR gate, the symbol looks like this. It's a little bit similar to the AND gate, but it's curved. It's got curviness. Let's compare it to the AND gate, which is boxy. It's straight, almost like a ginormous capital D. This one does not look like that. This one has the curviness going on. All right? I don't know how else to describe that. You're just going to have to memorize those symbols and be able to draw them. Again, we have 2 inputs and 1 output. But this time it's different. You might be able to guess what the OR gate does based on its name. If either A or B is high, then Y is high. Also, if both of them are high, then Y is also high. So, or we might say if these are both on, then Y is on. All right. So in this case, output Y is, you can see it right there, it's written out. The only time that output Y is low is when both of those inputs are low or off. So Y is only off when these are both off. Otherwise, Y is on. So that is your AND gate and your OR gate. And I'll just leave it there for a second so you can look at those informations. And let's look at our last 2, which build on these 2. The NAND gate and the NOR gate. All right, and the first thing you might notice is that they're exactly the same symbols as you saw on the AND and the OR, with only one change, and that's this little circle at the end. This little circle is the same little circle that you have at the end of an inverter. If you remember, the inverter was a triangle with the little circle at the end. The NAND gate is a AND symbol with a little circle at the end, and the NOR gate is a OR symbol with the little circle at the end. All right? So you might guess, if you're following along mentally, the NAND gate is an inverted AND gate. It's like taking an AND gate and putting an inverter at the end of it. All right, so it's exactly the opposite of AND. All right, so let's just detail what that means. when both A and B are high, then output Y is low. If you remember in the AND gate, when these are both high, then Y is high. But in the NAND gate, when these are both high, then Y is low. And here's the trick. Any other situation, then this output is high. So basically, when these are both on, this is off. If either of these is off, then this is on. All right, or both of them. If they're both off, this is also on. So the only time that this is off or low, the only time that happens is when both of these are on or high. A NOR gate is the inverse of a OR gate. All right, so let's see what that means. When both A and B are low, when these are both off, then the output is on or high. All right, so only when these are both low is this high. Otherwise, this is low. So basically, if this is on and this is on, then this is off. If this one's on and this one's off, this one's off. If this one's off and this one's on, that one's off. If they're both off, that one's on. All right, I know it's a little bit complicated. I wanted to just show you the basics of these gates. In the next video, we're going to talk about some truth tables, which will help you to visualize better with zeros and ones, and maybe, zeros and ones. It'll help you to visualize exactly what's going on with each of these gates, and it'll help you to figure out in various situations what's going to happen with these gates if you change the inputs or combine the gates together in certain ways. So that's for the next video. This one just introduced you to all the 5 gates and the idea of digital versus analog. So that's it for this video. Thanks for watching, and we'll see you in the next one.